is the public defense or VIVA of the thesis contact Hamiltonian systems that has been presented by Manuel Lainz to the Universidad Autónoma de Madrid to obtain the PhD degree. So the candidates.
Thank you very much. I'm going to discuss my thesis of contact Hamiltonian systems. This talk will consist in 3 parts. In the first one will be a small introduction on the relationship between geometry, dynamics, and variational principles. The second one will be a more technical introduction to my thesis completely, to contact manifolds and contact Hamiltonian systems. We will be covering both the Hamiltonian and the Lagrangian formalisms. And last of all, I will do a quick summary of the main publications and results that I have made for this thesis. So let's get started quickly. We will start with something very classical, which is the least action principle. One way to formulate theories in physics is to have an action functional, which is just a map that assigns to every possible path among 2 points, a number. This number is called the action, and the path which has least action will be the one that will be taken by the physical system. More precisely, we have a function which is called the Lagrangian, which is a function that depends on the positions and velocities of the system. Then you can consider the space of cubes that at a fixed time uppercase t, they last a fixed time uppercase t, and they have fixed endpoints. Then you can compute the action by integrating the Lagrangian along the cube, and you can prove the following result: a path, it's a critical point of this action map if it's only if it's a solution to these equations over here, which are called the Euler-Lagrange equations. This principle is very useful. Not only it's a nice mathematical tool to analyze the properties of these solutions. You can use it to prove the Netter's theorem, for example. You can use it to construct integrators for your system. But the problem is that not every differential equation arises from a maximum principle. For example, one of the properties of the solutions to this principle is that they preserve this function over here, the energy. But this means that you cannot model processes that do not conserve the energy, such as this one, which is the damped harmonic oscillator. One thing you can do is to add one extra parameter to the Lagrangian. So now it's not a function on the tangent bundle, but on the tangent bundle times r. Apart from positions and velocities, it depends also on one extra parameter. One possible choice is to take time as these extra parameters. Then, if you do a maximum principle again, you get the Euler-Lagrange equations, but now the Lagrangian depends explicitly on time. Another possibility, which is the one that we have explored in this thesis, is to take this extra parameter to be the action. And now you have an implicit variational principle, and the equations are no longer the Euler-Lagrange equations, but the Herlot's equations. This was studied by Herlot already in the 1930s, but this is probably one of this is the first modern account of this principle that we know. And here they already point at the relationship between the principle and contact geometry. Okay, so these are the Herlot's equations. They are similar to the Euler-Lagrange equations, this part over here, but they have these extra terms. That this term can add a dissipative behavior on some systems. And this other equation just says that the extra variable, the z, is the action because its time derivative is the Lagrangian. Okay, so the solutions of this equation dissipate the energy in this way. The energy always satisfies this equation. And indeed, for example, if we pick this Lagrangian over here, which is like the one for the harmonic oscillator in classical mechanics, but with this extra term, we obtain and we apply the Herlot principle. We compute the Herlot equation for this Lagrangian. We obtain the equation for the damped harmonic oscillator. Okay, so just to review it a little bit, in the case that we have a Lagrangian, depending only of the positions and velocities, a function of the tangent bundle, an autonomous Lagrangian, then applying the Hamilton's principle, we obtain the solutions of this principle are integral curves of a Hamiltonian system in on a symplectic manifold. Okay, you can play this game of changing the kind of Lagrangian and see what geometry you obtain. In the time-dependent case, the solutions are integral curves of a Hamiltonian vector field on a cosymplectic manifold. And for the action-dependent Lagrangian, you obtain integral curves of a Hamiltonian vector field on a contact manifold. And this would be what we will talk about during this defense. Okay, just to comment, systems that obey the Herlot principle appear on many parts of science. For example, in thermodynamics, the equilibrium thermodynamics is probably the one which is known for the most time. This traces back at least to Arnold, or you can argue that earlier. In other areas of physics, you can also get contact systems, like in quantum mechanics, geometric optics, cosmology, and as we said, dissipative mechanical systems. In control theory, in information geometry, and optimization and neural networks. Okay, the aim of this thesis, on the one hand, is to study more the geometry of the system and prove abstract theorems about the behavior of these systems. And on the other hand, to expand on these applications, try to see more things where you can see this contact structure and take advantage of it to know more how they behave. Okay, we will start with the second part of the talk. Here we will be introducing the mathematical framework we've been working with. First of all, let me define what a contact manifold is. It is just a manifold and a contact form, which is the manifold is subdimensional, and the contact form is just one form that satisfies this condition, that the form weights the differential of the form to the nth exterior power is a volume form. So this doesn't vanish at any point of the manifold, that is. And on a contact manifold, there is a unique vector field that fulfills these two conditions. This vector field is called the red vector field, and it plays an important role in contact geometry. Contact manifolds always have these local sets of coordinates that are called Darboux coordinates, in which you can write the contact form and the red vector field in this way. This implies that the contact manifold has no local geometry. Indeed, you can construct a diffeomorphism between any two contact manifolds of the same dimension that takes one contact form into the other locally. An example of a manifold which comes with a natural contact structure is this one, the cotangent bundle of manifold times R, which is also the first jet bundle of a manifold. And here the contact form is the differential of the R coordinate minus the pullback of the Liouville one form of the cotangent bundle. And indeed, the bundle coordinates for this manifold are Darboux coordinates. Okay. Contact manifolds are members of a class of bigger class of manifolds, which are Jacobi manifolds. And this is an interesting framework for us to analyze this geometry because it allows us to compare it with the other geometries we have talked about that are important for other kinds of dynamics. A Jacobi manifold is a triple of a manifold, a bivector field lambda, and a vector field E that satisfies these two integrability conditions over here. Given a contact manifold, we can define this map, which is an isomorphism of modules that just takes a vector field, so the contraction with the differential of the contact form plus the contraction with the contact form times the contact form again. This isomorphism takes the red vector field onto the contact form, and you can use it to construct a Jacobi structure for the contact manifold. You take as the vector field minus the red vector field, and as the bivector, you take basically the differential of the contact form composed with the inverse of this map. There is another picture of Jacobi manifolds, which is the Jacobi bracket. On the one side, you can use the contact. You can use the Jacobi structure to construct a bracket, which is a map of functions like this. It takes two functions and it gives another function. This map has these properties. It's bilinear, it's skew symmetric, and it satisfies the Jacobi identity. These three properties means that we have a Lie algebra on the space of functions, but this is a little bit more. This is what is called a local Lie algebra in the sense of Kirillov. And you need an extra property that you can choose many equivalent ones, but this one works is if you fix one argument, you get a first order differential operator. This is not a derivation, but it has this extra term. If the vector field was 0, this would be a derivation, and we would be on a Poisson manifold, but this is a little bit more general. Conversely, any bracket on the space of functions, which is a local Lie algebra on the sense of Kirillov, that means that it has these four properties. You can prove that it comes from a unique, from a Jacobi structure. You can put a Jacobi structure on the previous sense on your manifold, and then you get the bracket. Okay. More examples of Jacobi manifolds. Well, in the case that the vector field is 0, we just get the Poisson manifolds. Okay. And examples of Poisson manifolds are symplectic manifolds on even dimension and cosymplectic manifolds on odd dimension. And in the case that you have a non-vanishing vector field, more examples are the locally conformally symplectic manifold and contact manifolds. These two are especially interesting because there is a theorem that says that every Jacobi manifold can be foliated into leaves which are either locally conformally symplectic or contact. So if you want to understand the dynamics of Jacobi manifolds, these are the two more relevant examples. Okay, now we will talk about dynamics. In order to have dynamics, we need to equip our manifolds with a function. And now the triple formed by the contact manifold and this extra function is called a contact Hamiltonian system. We can use this function to define, and the Jacobi structure, to define the Hamiltonian vector field. In this works for any Jacobi manifold, not just for contact, but the contact is a specific case of this definition. In local coordinates, this vector field is like this. You can compare this with the Hamilton's equations. And if you see the first equation, the one for Q dot, you have Q dot equals the partial of the Hamiltonian with respect to the momenta. This is just like the first Hamilton's equation. But the second one, you have minus the derivative of the Hamiltonian with respect to the position, which also appears in Hamilton's equation. But you have this extra term over here, which is minus the momenta times the partial derivative of the Hamiltonian with respect to the action. This one is new. And you have another equation for the set, which is the action And this is basically the Lagrangian on the coordinates of the tangent bundle. So this just says that basically the differential of the action is the Lagrangian. This term over here adds a different behavior to our system, as we will see. For example, compared to Hamiltonian vector fields on symplectic geometry, you have very different properties. Now energy is no longer conserved unless the Hamiltonian is independent on the action, because this would be zero, but it dissipates at a rate which is just the red vector field applied to the Hamiltonian. The contact form also dissipates at the same rate over here, and the volume form, which is this one, this is a natural volume form on a contact manifold, also dissipates. In the case that the Hamiltonian does not vanish, which is not always, you can create this volume form, which depends also on the Hamiltonian, which is conserved. The existence of a conserved form, of a conserved volume form by on a Hamiltonian system is not an easy question, and the answer is not always affirmative. Even if the Hamiltonian vanishes, you can have a conserved volume form, but it is not this one. We will now talk a little bit about the dynamics of this vector field. So we consider the inclusion map from a level set of the Hamiltonian to the manifold, and we assume that, well, if we have a regular value of the Hamiltonian, then we can restrict the contact form to the level set, take a differential, then we get an exact symplectic form on this level set, which is exact because it's the differential of this one. Now you can take this Liouville vector field, which is the dual of the restriction of the contact form. This is a Liouville vector field, means that the derivative of the symplectic form by the vector field is the symplectic form again. It kind of scales the symplectic form exponentially. We have this theorem about the behavior. This was called in this paper the Liouville dynamics. Why? Because outside of the level set, the Hamiltonian vector field behaves as the vector field of this modified contact form, but that is you divide it by the Hamiltonian and then satisfies these two conditions, which is the ones that satisfy the red vector field. So this is the red vector field for this contact form eta tilde. And at the zero level set, something different happens. The flow of the vector field is just a reparametrization of the flow of the Liouville vector field, which you have this equation basically. The vector field is this function times the Liouville vector field. So you have Liouville dynamics, you have red outside the zero level set, and Liouville at the zero level set. Now we will enter on the Lagrangian formalism. Okay. Now Lagrangian is a function on the tangent bundle times R. Unlike the cotangent bundle, this has no natural contact structure, but we can use the structure of the tangent bundle and the Lagrangian to create one contact structure. Indeed, from these structures, you can create this form over here. And in case that the Lagrangian is regular, which means that this Hessian matrix of the Lagrangian with respect to the velocity is a regular matrix, then this is a contact form. And in that case, we can construct this map, which is the Legendre transform, which, if the Lagrangian is regular, will be a local diffeomorphism. And this map takes the contact form on the cotangent bundle to this Lagrangian contact form. Okay. And now we have a contact factor. In order to have dynamics, we need a function. This function will be the energy function, which is this one over here. And if you compute the Hamiltonian vector field of this energy function with respect to the Lagrangian one form that we have just defined on the previous slide, then we obtain what we call the Herriot vector field of the Lagrangian, this one over here. And if the Legendre transform is a global diffeomorphism, then that takes a Hamiltonian into this energy function. This will commute these equations of this vector field over here will be taken onto the Hamiltonian vector field on the cotangent bundle. Okay, and this vector field over here is what we call a second order differential equation on a slightly generalized sense. We mean that the integral cubes, this is the part on the positions, on the velocities, and on the action, satisfies that the part on the velocities is the time derivative of the part on the positions. We don't assume anything about the part on the action, and these integral cubes, the part on satisfy the Herriot's equations over here. It's a second order differential equations, first order instead. Okay, so this is connected to the variational principle we were talking at the beginning of the talk, that we will now explain with a little bit more of detail. Okay, we consider the space of cubes which go onto the configuration space and a real number which will be the action, and we will put it boundary conditions on the part of the configuration manifold and just an initial condition for the action. Okay, we will restrict this space of cubes to the ones that the time derivative of the action is the Lagrangian, as it should be, and then we can define an action just like this, as the variation of the value of set from initial final minus initial. Also, by the fundamental theorem of calculus, this is the integral of the derivative of the action, which by this condition we have put here is also the integral of the Lagrangian. This clearly, in the case that the Lagrangian didn't depend on this action, would be just the Hamilton's principle action. Okay. Now we have the following theorem that you can prove by doing a little bit of variational calculus. A path is a critical point of this action if and only if this is a solution to the Herriot's equations, which are these equations over here. Okay. Now we will just state one basic result on this Herriot equation, which really is striking if you compare it to the classical setting. In the classical setting, Noether theorems are theorems that usually, well, Noether theorem and generalizations are theorems that they link symmetries on your system with conserved quantities. Probably the simplest formulation of this theorem is once you have what's called a cyclic coordinate. If the Lagrangian does not depend, assume this is zero, assume that the Lagrangian does not depend on the action, and we are in the Euler-Lagrange equations. If the Lagrangian didn't depend on one coordinate, then we would get that the derivative of the corresponding momenta is zero. This is maybe the basic question. If you have a cyclic coordinate, the corresponding momenta is constant. This is okay. Here it is not the case, as you can see. Assume that, for example, the Lagrangian doesn't depend on the first coordinate, on Q1. Okay, you take this equation over here, and here you would get a zero. So what we get is that the time derivative of the first momenta is equal to the derivative of the Lagrangian with respect to the action times the first momenta. Now it's no longer zero. This derivative of the Lagrangian with respect to the action is also minus the red vector field applied to the energy. So now this momenta is not conserved, but it is dissipated at this rate, okay? So we can generalize it and extend it to the Hamiltonian formalism, and we can say that a function is an age-dissipated quantity of this system if and only if it has precisely this relationship. It dissipates at a rate which is minus the red vector field applied to the Hamiltonian. This can be formulated also in this bracket formalism by saying that it commutes with the Hamiltonian with respect to the Jacobi bracket. A quick comment that if the Hamiltonian does not vanish, but the Hamiltonian, of course, commutes with itself. So the Hamiltonian is the first example of an dissipated quantity, as it is a conserved quantity on symplectic systems. And since all dissipated quantities dissipate at this rate, if you take the quotient, you get a conserved quantity. So you can also use these dissipated quantities to get conserved quantities on some situation. Okay, now I will state one version of these Netter theorems. We have many of them on the thesis, but this is general, a simple one. Assume we have a vector field that has this relationship. It's what's called a conformal infinitesimal contactomorphism. If you take the derivative of the contact form, it gets multiplied by a function. Then function you get by contracting the Hamiltonian this vector field with the contact form is dissipated if and only if the Hamiltonian is F dissipated, or like this. Okay. And a simple example of this theory is the harmonic oscillator with dissipation. We have this Hamiltonian, like the one for the harmonic oscillator, but with gamma times the action as an extra term. And we have these equations of motion. The moment, the position is the same. There's the momenta is mass times velocity. The one for the momenta is you have minus a constant time the position, which is also this is the classic harmonic oscillator. But we have this extra term, which is a friction proportional to the momenta. And the last equation just says again that the time derivative of the action is the Lagrangian. We can also see it from the Lagrangian side, which is like this. And one interesting thing is that this system has a dissipated quantity apart from the Hamiltonian. This is not the case for the classical harmonic oscillator. And it is this simple quantity, which is just the action minus the position times the momenta divided by 2. Okay. Now we're entering the last part of this talk, which I will just mention all the publications of my thesis and some of the major results. Okay, let's get started by our first paper. This is a work that we started when I was in master's here at IGEMAT also. Well, Manuel Lainz, basically, because I have no idea what a contact manifold was at that time, noticed that there was an interest on contact systems from the applications perspective, which was, well, among the papers that we read, a very interesting one, which was this one by Alessandro Gravetti, published in Entropy. And we thought about proving some results on these systems. The aim of this paper was to prove a coisotropic reduction theorem, but we also ended up making kind of a review of the results of contact Hamiltonian systems and we saw them, we compared it with other geometries in the context of the Jacobi manifold. We proved this coisotropic reduction theorem, and we used this coisotropic reduction theorem to prove a Marsden-Weinstein kind reduction theorem, which this theorem was already known the new thing was proved using this other theorem. And this paper, I think it was quite successful. It has now, but it was an editor pick of the Journal of Mathematical Physics, and it has over 70 citations on Google Scholar. I think I'm not going to stop much on these theorems. If you are interested on them, maybe you can ask me afterwards. The next thing we did was the Lagrangian formalism, which was in this paper, Singular Lagrangian and Precontact Hamiltonian Systems. Here, we introduced the contact geometric Lagrangian formalism with this Lagrangian contact form and the Herlop vector field. We also consider the case of singular Lagrangians, that the Hessian matrix is not regular. And we develop a constraint algorithm to deal with these dynamics. And we also introduce a Dirac-Jacobi bracket, which is a modification of the Jacobi bracket of the contact system that you can use to study these singular dynamics. After that, we studied the relationship of symmetries with dissipated quantities. Well, at the beginning, we were trying to find conserved quantities, but we find out that it was not working well. It was not possible, and we should take the dissipated quantities. We have classified symmetries on both Lagrangian and Hamiltonian formalisms and have conservation, or what better said, dissipation theorems for all of them. This was done in this paper in infinitesimal symmetries in contact Hamiltonian systems, but also I think this citation is not appearing completely. No, but there is also a paper by Jordi Gasset, Xavier Gracia, Miguel Muñoz Lecanda, Xavier Rivas, and Narciso Roman Roy. They also were working on these symmetries, but just on the Hamiltonian formalism. Okay, another thing we have studied is inverse problems and equivalent Lagrangians on the contact setting, on the action-dependent setting. It's a problem which is much more subtle than on the classical case. Having equivalent Lagrangians means that you have two Lagrangians that produce the same dynamics. You have to be careful what you mean by the same dynamics. It can be taken on many formalizations. And the inverse problem is related to these problems, and how it just means that they give you a dynamics, and you have to determine if this comes from the Herlop principle or not. A partial solution of this problem in the classical case is the Herlop condition. The Herlop condition are just some equations on the coefficients of your system that if they satisfy these conditions, you can say that these dynamics come from a variational principle or not. We have not been able to do that on the action-dependent setting, but we have some partial results, and I think we have the right formalization of this question. But what we've been able is to obtain, I think, a quite complete characterization of equivalent Lagrangians. Basically, two Lagrangians are equivalent, they have the same dynamics if there is a function that satisfies this relationship between the two Lagrangians L and L bar. You see that in the classical case, two Lagrangians are equivalent if they differ by what's called a total derivative, which is a term with this sense. In the case that this function is just set plus a function of Q, you get you recover the classical result, but this generalizes it. Another thing we've worked in quite a few times with this is the relationship between contact systems and constraints. First, we introduced contact systems with non-holonomic constraints, which are a non-holonomic variational principle for constraint systems, which is a principle that has applications in mechanics. For example, if you have friction, something like that. And also we have studied baconomic constraints, baconomic systems, which have applications in control. For the non-holonomic dynamics with linear constraints, we define an almost Jacobi bracket which describes the dynamics of this system. Almost Jacobi means that it doesn't fulfill the Jacobi equation, the Jacobi condition, the bracket, but it does satisfy the rest of the other four. Apart from this, we also saw that contact systems themselves can be seen as symplectic systems with extra constraints, and these constraints can be taken to be baconomic or non-holonomic. These are the three papers. The first one is non-holonomic, the second one is baconomic, and the third one is all of the above, basically, and considering also contact systems and as particular cases of constrained symplectic systems. These are the equations for the baconomic principle, and these are the one for the non-holonomic principle. Another thing we have worked in is higher order contact mechanics, which is that now we let our Lagrangians to depend not just, well, apart from, they can depend on the action, on the positions, on the velocities, on the accelerations, and on higher derivatives of the positions. Here you get these equations. If your Lagrangian depends on k derivatives, then the equations should be of order 2k, and they have this structure with this thing over here is the what we call the Herlot operator. If you see in the case k equals 1, you recover the Herlot equation, but well, this gets very complicated once you get higher order. We also these systems also have a Hamiltonian formalism that we have also explored. Okay, other things we've worked in are other formalisms for mechanics. One of them is the unified formalism, which is a formalism that includes both the Hamiltonian and the Lagrangian formalism, and it takes place on the Whitney sum of the cotangent bundle, the tangent bundle, and the action and R. Okay. We also introduced the Boursier formalism. In this formalism, the dynamics are just special kind of submanifolds on contact geometry, which are called the Yevnian submanifold. This formalism is especially useful when you have singular or constrained systems, because you only deal with submanifolds, not with well, with vector fields. You can have more problems. This is the Boursier triple formalism. Basically, this is the Hamiltonian part. This is the Lagrangian part, and you have these isomorphisms, the alpha and the beta, that takes the dynamics from one of these manifolds to another. They are all represented as submanifold. They can be images of the Hamiltonian vector field they can be images of one jets. Okay. The last thing, the last theoretical thing we have worked in is the Hamilton-Jacobi theory. The Hamilton-Jacobi theory allows to understand the dynamics of your system by solving a PDE. And here in contact manifolds, there are two Hamilton-Jacobi theory, depending if you allow the section to depend on the action or not. This is the first Hamilton-Jacobi equation. Okay, this equation just tells you when this diagram commute. If this diagram commute, you can solve the dynamics here with a vector field projected to the configuration space and use the section gamma to reconstruct the dynamics on the full cotangent bundle times R. Okay, in this case, the equation is this. If this is satisfied for the section gamma, then you can do this. This diagram commutes. In the case that the section gamma is allowed to depend on the action, now before it was a section from Q to the cotangent bundle times R, and now it's a section from Q times R to the cotangent bundle times R. Okay. Now, for this diagram to commute, this equation has to be satisfied, which is slightly more complicated, but this is also, these solutions are a little bit more useful. Okay, apart from this more geometrical part, we have also worked on variation integrators on this and discrete geometry of this system. We have helped to develop a theory of discrete mechanics based on a discrete version of the Hertz principle. We have introduced the exact Lagrangian, which I will explain now what it is. And we have also studied discrete symmetries, and we have a discrete version of the Netzer theorem. The first time this discrete Hertz equations appear, as was in this paper over here. This is our paper on this discrete contact mechanics. In the discrete contact mechanics, you have a Lagrangian which is not defined on the tangent bundle, positions and velocities, but in two copies of the configuration space that you can think of as the initial and the final position times R. Okay, and here again, you have now discrete parts that are just collections of points on the configuration space that you can think of as steps, as the position of your system one time step. And then from a discrete path, you can obtain a discrete action by solving this difference equation now. So it's a difference equation instead of a differential equation. And you define the action of the path as the initial, as the final set minus the initial set. Now, the critical points of this action map are the solutions to this discrete Hertz equation over here. Okay, the main contribution from that article, from my point of view, is the construction of this exact discrete Lagrangian. If you have an action-dependent Lagrangian, like a normal continuous action-dependent Lagrangian, and you fix a time step, which is small enough, and you work locally, then you can construct a discrete Lagrangian, which gives you exactly the dynamics of this Lagrangian over here. And basically, the solutions of the discrete Hertz equations for the discrete Lagrangian are just the solutions for the Hertz equation for the initial Lagrangian evaluated at the time step A. We think this theorem can be used to get better integrators by trying to approximate this Lagrangian. And last of all, we have worked on applications of these contact systems. One of our main contributions was the introduction of the evolution vector field from the this is also geometry from the symplectic, from the contact structure of your manifold and the Hamiltonian function. Apart from this vector field, you can also define this one, which gives you similar equations for the integral cubes, except this last term. And apparently, this vector field can be used to describe processes in non-equilibrium thermodynamics for isolated simple systems. This one over here. And this was published on the Proceedings of the Royal Society. And last of all, we have also worked in control theory. We have studied a control problem in which the Lagrangian depends on the cost. This can be thought as a generalization of the Hertz principle, so we call this the Hertz control problem. And we proved a contact version of Pontryagin maximum principle. And well, this is the Hertz control problem, and the solutions of this principle are the solutions of this problem are the cubes that satisfy this thing over here. These are the optimality conditions for the optimal control problem if you take f to be independent of an xj independent of z. If you remove all these terms, you get the usual optimality conditions. And well, this was the whole talk. These are just the references I've been talking about during the presentation. And okay.
So thank you so much. We now go into the discussion.
Yeah.
So I will call the members of the panel successively, and they will each ask questions or make comments, and then you will answer them.
Okay.
So first, Dr. Garcia.
Yeah, sure. Thank you. Well, first of all, congrats on your thesis. It's a very nice work, and also to your supervisor. I was impressed by the number of publications that you have. Quite a lot. So I had a few questions. Very nice, because I'm not an expert.
Okay.
But one of the main objects of study your thesis is Hertz's equation.
Yes.
Can you say a word on how do you derive it? I mean, you have explained it, but one thing I don't understand is why you restrict to curves such that its derivative is the.
Yes, basically there are many ways to do this. I have a couple of them, I think, in the thesis. Basically, you need an action. Okay, some derivation.
Maybe you can minimize it.
Yeah. I think we should. Here. Okay, there are many ways to do this. I chose this one because I think it's the simplest one. But basically, you need to have an action-dependent Lagrangian, and you need some way to formalize what an action-dependent Lagrangian is. And if you want something to be the action is the integral of the Lagrangian, right? But the Lagrangian also depends on the action, so you cannot solve that integral. You can take the time derivative, and then you have that the time derivative of the action is the Lagrangian. And you can take it as a constraint. You can just define the action on the paths, and then solve this, treat this as an initial value problem and solve it. So this means that this is just, I am just requiring this set to be the action. This is what this constraint means.
Maybe my question is,
It's not
so
what.
do you know that, is it known a priori that Carnot's equations are the right model for some physical models which dissipate energy? And then this is a way of deriving these equations, or there is an underlying principle?
No, there is a principle. This is a variational principle. Maybe it's written in another way on the thesis. It's on chapter 3. On chapter 3, you can write this as a principle for cubes also only in Q, if you prefer that. But I don't know if this. This is a variational principle, and from this you obtain the equations. It's just that instead of being given by an integral, it's given by an ODE, because now the Lagrangian depends on the action. I don't know if I can explain myself correctly.
Yeah, and just another question I had is related to this. You emphasized at the beginning that whenever you have a contact Hamiltonian system, you have a volume which is not the natural volume, but rescaled by h, which is preserved. How do you use that? Why is this important?
No, I didn't use it.
Okay.
I haven't used it. Actually, one of the things I've noticed, like most of the times, in these contact systems, it's usually better to work with dissipated quantities than with conserved quantities. So this volume is dissipated.
Yeah. Another question I had is regarding your theorem about reduction. It's 4.47. I think
47.
Yeah. So I'm familiar with the usual framework of symplectic reduction, but not with this. So one interesting thing for me is that so this is in page 86.
Yes.
That you require the Hamiltonian to be invariant under the action of the group.
Yes, here it's required.
Yeah, but then in symplectic reduction, this means that if you take the Hamiltonians of all the infinitesimal generators of the action, this is going to commute with the Hamiltonian vector field generated by H. But here, if I understood properly, so the Jacobi bracket of H with any of these Hamiltonians generated by the action is not zero, right?
In this case, it is, because this action preserves the contact form exactly. So this is equivalent, like this. The flow of this, basically the action is the flow of Hamiltonian vector fields that do not depend on Z. So this commutes because they are zero if you apply the vector field to them. In this case,
then I understand. Okay, because I was confused. That
maybe you can have a theorem in which the group acts by a more general contact, by conformal contact homomorphisms in my language, and then the condition should be a different one probably, but I haven't checked that.
Thank you. And yes, my final question is for the future, maybe. So, yes, I'm curious about whether there is anything known about quantization for contact Hamiltonian system. Is there anything done in that direction?
This is something we can study. Another thing we are studying is this extension of this principle to fields, to field theory in which the Lagrangian depends on the action. This is something which is called the action flow, or the action in this case. In contact systems, the quantization is something that can be also studied. This is a open problem. Also, this inverse problem for contact dynamics I think it's still quite open. You can also construct better integrators, generating functions, there is these two things to work in this field, just from the theoretical perspective. Also, you can always find new applications of this system.
So thank you. I don't have any further questions.
Okay, thank you.
Thank you. Now, Dr. Bravetti, your turn.
Let's hope.
Thank you. So Manuel, first of all, again, congratulations on your work. And I have a few questions, but maybe the first one, also with respect to your presentation, is the fact that I have this feeling that you've done a lot of work and you've explored several directions in this field. So I wanted to ask, what is, in your opinion, if you could give us a summary in which you give us the two most important achievements, like the one for the theoretical side and the other for the application side. So I know it's a general question. Later, I will have more specific ones, but it's a need that I have for summary.
Okay, I can tell you the things that I think I'm most proud of. From the application side, I think probably one of the biggest achievements is the introduction of this evolution vector field, because it's something that if you like, it's very easy to define. It's just a small modification of the definition of the Hamiltonian vector field, but this behavior is completely different. And you see the correct the chapter, you see that they have properties that has nothing to do with the Hamiltonian vector field, and it also turns out to model some non-equilibrium thermodynamic systems, which is very interesting. This was an easy result. From the theoretical side, I cannot decide between two results, which I think I don't think if they are the most important, but they've been the most difficult for me. One is this one, the constructions of the isomorphism of the 2CF triples, especially this alpha isomorphism. I tried to do this during the end of my master's thesis. I was unable to, and then I tried again 2 years later, and I finally could construct this isomorphism. It was like a very interesting process, because I was like requiring properties to this map, and I just saw that if this exists, it has to be this one. Then you compute the pullback by hand, and you see that you get the right equations, and this is also pretty like, it was like a nice moment. And another one that I am proud of is this thing, how the exact discrete Lagrangian, which, if you think about it, it seems that it should be something trivial, but it is not, and the proof, it's not very direct, it's very geometric, not very analytical. We move to a higher dimensional space, we solve the problem there, and then we go back using the Hertz principle. I think these are maybe my favorite results.
Okay, thanks. It's nice that you mentioned two of the things that I wanted to ask later. So for the first one, this evolution vector field, in the thermodynamic context, of course, it has some properties that are very similar to the properties that one asks usually within this generic formalism. I don't know if you've heard of it. If you had, sorry?
Yeah, indeed, you can relate this formalism to the generic formalism. I think you can construct, more specifically, you can construct the brackets of the generic formalism from an evolution vector field. We dealt with this I think in the first paper.
Oh, okay. That was precisely my question. So you've already answered that.
Yeah. I think maybe in the thesis not explained with so much detail, but here we compare this formalism with the generic formalism. and this can be considered a particular case. Also, this has a richer geometry than the more. You can know more about the behavior of a system by knowing that it's an evolution vector field than by knowing that it's a generic system. You can prove more specific theorems to this kind of system for this kind of systems than for the more generic ones.
Sure. Okay, that's very nice. And then there was another question regarding this vector field. You mentioned that you wanted to explore the generalization of contact Hamiltonian systems to field theories. So yes. There's an open question, I guess, whether one can generalize also this evolution vector field. Have you thought about that?
Yes, this is something that I have on my mind. But first of all, I think I will try to upload to the archive a paper about the Hertz principle for fields in the following, let's say, week. To not put myself on a hard compromise. And after that, we also have to understand better the geometry of these systems. And then one thing that I am thinking that these systems might be good for as precisely non-equilibrium thermodynamics, and maybe you need an analog of this evolution vector field, be an evolution field, or I don't know exactly what, or maybe it doesn't make sense. I don't know. This is a very open question. I still don't know what's the analog for fields of contact systems. So this is too soon to answer this question. But maybe
yeah, exactly. That's what I was referring to in order for studying non-equilibrium thermodynamics by field theories. So thanks. And maybe a last one, just not to ask too much. Regarding the Hertz principle, I want to know if you have any ideas. This is more on the physical side. If you have an intuition why for dissipative systems, at least for this class of dissipative system, one needs the action to be action dependent in order to model the system. It seems very strange. Well, mathematically it works. And it's maybe related to the very first question that's been asked. But do you have any intuition why physically it should be so?
This is an interesting question, but actually I'm not sure if I have an intuition why systems in classical mechanics satisfy the usual distraction principle. For me, this is just like magic almost. So I don't know. I have no idea it works for now until I have a better answer.
Yeah, you've explained more or less already with the comment what is my point. The point of the question is that usually, at least to me, from the physical perspective, the action is something very mysterious, also in the symplectic case. So that's why I'm trying to figure out, and that's why I was asking you if you have an intuition. If maybe from this different perspective, one can explain physically the appearance of the action.
I'm hopeful that you can maybe get something by the, if you can understand non-equilibrium thermodynamics, maybe this has some thermodynamic interpretation in its action or something like that. But just from mechanics, I think it's I don't understand. I'm not. I wouldn't know what to say. Like why the action, the Lagrangian depends on the action, because both the Lagrangian and the action are quantities that are not measurable. They have a very hard the physical interpretation. It's not something that you can measure on the lab, basically.
Sure. Well, thank you very much. That's all of my questions.
Okay, thank you, Professor Bravetti.
So now I call on Dr. Nunes da Costa.
Thank you. Can you hear me, Manuel?
Yes.
Okay, so first of all, I want to start by congratulating Manuel for this excellent work. I was very impressive because in a very short period of time, you have so many publications, all of them so interesting and with many original results. The fact that you have so many publications was not easy for you to organize all these ideas and results to have a piece of work that made sense, and I enjoyed very much because you were able to organize things in a very coherent way, and it was very nice to read the chapter after chapter. So maybe it was not an easy task to organize so many papers concentrate them in a thesis. I also want to give a word for the also very impressive list of references you have. You have more than 200 references in your thesis, which is remarkable. Well, I don't have too much questions. I was mainly focused in the first part, since I'm a mathematician. I'm not a physician. I was very interested for the theoretical results that you have in your thesis. And I just want to ask you about a theorem in chapter 4, a reduction theorem. I mean, so page 93. So 93. So the compact version of Marsden-Weinstein reduction theorem.
93. Sorry.
Okay, my theorem 4.46. I don't know if my pages agree with yours. So
yes, 46.
Yes, so the reduction theorem via moment maps. Okay. So before this theorem, you gave another reduction theorem for coisotropic reduction, right?
Exactly.
Yes, and then you give this Marsden-Weinstein reduction theorem for compact manifolds, and you give a new proof.
Exactly.
And for that, you have to place in a particular case. I mean, the
yes.
isotropy group is the whole group G, right? G mu equals G.
Yes.
Okay, this is a bit restrictive because you have not taken the case where mu is just a regular value. I mean, the isotropy group is strictly contained on the Lie group G, the big Lie group. My question is, I understand that you have considered the particular case in order to get a new proof for this classical result.
Exactly.
But, yes, but it seems for the reader that this theorem does not work for compact case in general.
Well, the point of this, our result was the result of coisotropic reduction.
Yes.
This one, the theorem, I don't know, theorem 441.
Yes, I understood. You wanted to use your theorem on contact coisotropic reduction to create a new proof of Marsden-Weinstein. My question is, in the general case where mu, where the isotropy group of mu is strictly contained on G, on the big Lie group G, is it possible to reduce a contact structure and to get another contact structure? This is true for Jacobi structure, right? But contact is a particular case of Jacobi.
Yes.
This is my question.
Well, if it's true for Jacobi structure, then it has to be true for this case. Oh,
Yeah.
sorry, no, you can get a manifold which is Jacobi but not contact. Here we only restrict to the level set of the moment map. On the whole manifold, you have a contact structure on each of the level set, but you cannot base it to sustain a contact structure, but a more general level structure. But yeah, I am not really sure if this, like, I haven't worked on this since this first paper we did in.
Okay, so no problem. So
This was just an example of the applications of this.
yeah, I know. This is a bit aside of your thesis, but since I have been working in this type of reduction, I was wondering why didn't you mention that in the general case you could do also the reduction? Okay, but it's fine. And another related question. As I said, this section 4.5 that deals with reduction, right?
Yes.
It seems that you didn't apply it too much. It is not useful for this type of studies to work on, let me say, smaller reduced systems, get the desired results, and try to lift up to the initial one.
You mean that I didn't use the reduction theorem, this Marsden-Weinstein type reduction theorem? Or
no, I mean the idea of reduction in general.
Reduction. Well, if you are working with a complicated system which has a big group of symmetries, of course you can reduce it, work on the reduced system, and there is a way to reconstruct the solutions. But I haven't worked with many concrete systems, and all the examples are not very difficult. So the examples are mostly toy examples here of the reduction. I don't have anything very complicated. So maybe
okay. So it is not so useful to use this reduction procedure to.
Saying that it is not so useful is that
Yes.
I don't encounter systems where which have this thing that they have a very big group of symmetries and they were very complex. If you have one of these systems, probably it is useful, but it hasn't been my case.
Very well. Okay, so regarding questions before I made some comments. This is a big general question, but do you think it's interesting or useful, or have you thought about working on what is called contact fiber bundles? These are structures that were introduced by Eugene Lerman in 2003. So mainly you have a fiber bundle, each fiber has a contact structure, and in some conditions you can get also contact structure on the total space of your vector bundle. So it is a more general picture. I don't know if it has some interesting applications in what you are doing, but I think that at least some of your theoretical results could be seen in this framework of contact vector bundles.
Yeah, I'm familiar with these contact vector bundles, but I don't know if they have some applications. So I wouldn't know in which kind of system this structure would appear. And I think in order to work on these structures from a theoretical perspective, that probably maybe even if some theorems are still applied to the situation, there will be a little bit more involved to prove. I would need to see some applications of these systems in physics or other science in order to get interested in them enough to write papers with these systems in mind. I don't know what kind of systems that you can have. They are like composed systems somehow, maybe something related to non-equilibrium thermodynamics. I will think about it, but so far I haven't found any applications of this outside of geometry.
Yes, that's what I think. For application, it will be very difficult to find examples, but at least you have so many interesting theoretical results on contact structures that I think that, for instance, some of the results you have in chapter 4 regarding symmetries and so on, they can be seen in this framework. That's what I think. I just now want to make a comment. As I said, you have a very good thesis, and I enjoyed a lot the organization that you were able to do in order to fit all your results in this thesis. But I should say that I don't know in Spain what is the common thing to do after your defense. Is your thesis going to be published online?
Yes, I actually want to publish this on the archive because it's where I think people will find it. It's already published on the university page and on the
Yes.
I'm not sure.
Okay, so if you are going to do this, I should say that the first part that I read it very carefully, and I found many misprints. Sometimes the notation is not consistent. This is because maybe you have so many papers and there are not exactly the same notation that you have used. For instance, I mean, sometimes most cases in your papers you use H for the Hamiltonian function, but in some results you use the F as a function, and here in your thesis it's a bit mixed. Even inside the same proof, you start with H and then you pass to F. And well, I should say that while at the beginning of my reading, I noted all misprints, but then I gave up. But at least for the first chapters, if you wish, I can make a list of misprints that I have found in order that you correct them before you publish online, if you want, of course. And also some signs. And the curious thing is that in some cases, I went to the source. I mean, I went to the paper and the misprints are already in the papers. So which is a bit curious. But for instance, in order to see what the type of things that I'm saying, for example, in the very beginning, proposition 2.11, This is for the Jacobi
2.11.
2.11. Page 43. Page 43. So,
I don't think that we have the same.
okay, so 2.11.
2.11.
Okay, so when you express the Jacobi bracket on contact manifolds, so that the signs are not good because the rep vector field is minus the Jacobi vector field. So you have to change the signs in equation 2.76. You see the statement of your theorem.
76. No, this
Yes.
is okay. Well, which one is incorrect?
The statement of your proposition 2.11, you have the wrong signs. Okay.
Where?
Equation 2.7.
All right, the F.
Because the red vector field is minus E. So
The
you
left
have to
is
change.
correct, but the ones in the middle. Yeah, this is. Yeah, I mean,
Yes,
this
these are but
you find plenty of these.
yes, there's a many type of things like misprints like this. For example, in the same proof, there's a minus missing in the equation 2.79. Yes, it is a minus missing.
Minus missing, yes.
Yes, and then the same at the very last line of the proof, which is a bit strange because this comes from the previous line, and so this is a misprint. So there are many, you see?
I have to change these signs many times to match all the signs convention that I have used.
Yes,
I
understand
wouldn't be
now.
surprised. I've made some mistakes. But
Yes, but let me tell you that you should read, because I found a lot of cases like this one. Of course, it is not very important, but
if you have found some of these ones, I would be very happy if you could.
yes,
At least
Yes.
before, like now in the university archive, I think it's already fixed, but I can upload a corrected version to archive.org, and which I think is what people will actually read. So
okay. I as I said, I marked some of the misprints I found in the first chapters, but then I gave up. But at least those that I have marked, I will send you, okay? In order that you, before you put it in the archive, you can correct.
okay,
And that's all. I was very happy to read your thesis, and congratulations again.
okay, thank you very much.
Thank you. Now, Professor Marmon.
Oh, Marmo,
Yeah.
okay, so you
Okay, because you okay. Well, I have been discussing directly with Manuel in Madrid when he was there a couple of months ago. I was a little surprised that many of the misprints, as Johanna was saying, which had been noticed already at the time, are still present in the thesis now. But I understand that cutting and paste usually might give these problems.
I try to correct them.
Well, let me go to more specific questions.
Okay.
You see, with respect to the Euler-Lagrange equation that you get out of a Lagrangian, which are linear in the Lagrangian, the Hertz's equation are not linear in the Lagrangian.
Exactly.
So this means, for instance, that if you take a Lagrangian and you multiply by 3, let's say, the equations of motion, the Euler-Lagrange equation will still be the same, but this is not true for Helmholtz equation.
Exactly.
So now you already mentioned in answer to Alessandro that the Lagrangian and the action are not measurable. Well, in quantum mechanics, what happens that if you, for instance, multiply the Lagrangian by 3 and you apply Bohr-Sommerfeld principle, then the trajectory which are selected as a quantum trajectories, let's say, whatever that may mean in the old quantum theory, they would be different. So this is the first example where you have a situation, a physical situation, where the result is sensitive to the Lagrangian, is sensitive to the fact that you may multiply the Lagrangian by 3, let's say. The other comment is that usually Poisson brackets are limits of quantum commutators, either in the Dirac approach or whatever approach you may consider, let's say deformation or others. Poisson brackets are usually the first order approximation or the first order limit of quantum commutators. Now, a natural question would be, Jacobi brackets are the limit of which object in the quantum setting? Now, this obviously, I don't expect that you have an answer, but I think it's an important question to ask and to try to solve. What I'm trying to say here, that while action and Lagrange are not measurable in a classical setting, they are in a quantum setting. Indeed, Planck's constant is the unit of action.
Yes.
So this means that perhaps one should pay more attention to the quantum to classical transition. And the other comment, which seems to me, you give an example of a compact symplectic manifold, which is a spinning particle. By the way, you introduce in the introduction the notion of classical spin. I don't know what is the meaning of classical spin, but nevertheless,
Gave the citation. I think it's an Arnold's book, if I'm not mistaken. But it just means that it's just a system on the symplectic sphere.
yeah, what I mean is that this would be a spin 1/2 particle.
Yes.
But obviously, if the spin is different from 1/2, let's say, then you would have a manifold of different dimension, which need not be a sphere. Indeed, there's an example of a manifold which would not be an exact contact manifold, is the family of normalized states in quantum mechanics. So if you take, let's say, a finite level system, the manifold of normalized state
Sphere.
is a sphere. It carries a Jacobi bracket, but does not carry an exact contact structure. So this would imply that one should go beyond exact contact structure. That is, you would need a notion which is more general than the contact one, because obviously having the Jacobi bracket, you can still talk about evolution equation, Hamiltonian vector field, and so on. You can actually show that on the space of pure states, you can describe dissipation. And even though the manifold is not a contact manifold. So I am wondering, in a sense, if one as a general comment to the, if one should not go beyond conduct Hamiltonian vector field in the sense of exact contact.
I see. This is something I also thought about. Actually, if you see like remark 2.1 and 2.2 of the thesis, I make a comment on these situations. I think you can carry out most of the theory, but you have one issue, which instead of having contact like Hamiltonians as functions, you need to have sections of this bundle. And from here, you can use the contact form to define a Hamiltonian vector field. I think yes, this is the right bundle. Well, this is the right bundle. No, this is the right bundle. Yes, the problem is that I think this complicates the treatment of this theory quite a bit. And well,
let me say, I disagree with what you are saying, because quantum mechanics can be formulated in terms of function. It's true that the formulation in terms of sections of a U1 bundle may help in describing the way that an overall phase does not affect probability transition. But you can simply introduce a Kähler space, a Kählerian manifold, let's say. This would be the space of pure states, but this would also be symplectic. But if you go to the space of normalized states, then there the Hamiltonian function is well defined. There is a Jacobi bracket, so you can define all the bracket you might want to define. Essentially, the Reb vector field is simply what would be the Hamiltonian vector field in the ambient symplectic space associated with the probability function. That is, you take the norm of a vector, you think of it as an Hamiltonian. The Hamiltonian vector field will be restricted to the unit sphere, let's say, and then this is going to be the Rib vector field. So as long as you take functions which are invariant under this vector field, obviously you get back the Poisson structure, the Poisson bracket. This is obvious also from your treatment. If you take function on which the Reb vector field vanishes, then obviously the Jacobi bracket becomes the Poisson bracket. And this is actually one way to get the space of pure state as a quotient by the Rib vector field. So it is true that in general, in infinite dimensional manifold Hilbert spaces, let's say, if you realize the wave functions as functions on a Lagrangian submanifold, then it would be useful to think of them as U1 sections. But you can work at the level of the total Hilbert space. You restrict yourself to the unit sphere because this is what the Born interpretation rule for probability requires. And this space carries a Jacobi bracket. And this is what you could go on, and there are no complications of the way you are mentioning. So in some sense, while it is true that you could work in terms of section, but working in terms of section would be an artifact because the total space is well defined. It's only restricting functions to the sum-manifold of normalized states, which is a very good concept, a very well-defined concept. And you can carry on your argument. You can define your evolution vector field, your Hamiltonian vector field,
Also
exactly the way you have done.
with this, yeah,
Sorry.
no, sorry, you're asking. No, I mean, this, I have also a problem with this formalism in which we work with the distribution instead with the contact form, is that I don't know what's the Lagrangian theory, which is formalism. How can you set up?
The Lagrangian would be highly degenerate.
Yeah, this
The
is
reason is that obviously Hamiltonian quantum mechanics is described by first order vector field. So you cannot try to write a second order vector field. You should accept that the Lagrangian that you may write to describe the equation of motion for quantum system is not going to provide a second order vector field. I think this business of the second order vector field is a red herring. I mean, usually for instance, in quantum mechanics, what Dirac had in mind, obviously the dynamics, it's only required to be first order dynamics. I mean, Heisenberg equations or Schrödinger equation, they are first order differential equation in time. And so from this point of view, there is no need to go to the second order problem at the quantum level.
yeah, there is a need for the applications. For example, you can have these variational integrators because you have a vector field. If you didn't, then if it was a degenerate system, then you couldn't have these discrete integrators, which are useful for the application. So these extra complications are some of the reasons where I choose the setting with a contact form. Anyway, most of my results are local, so they could be extended to this more general setting without much difficulty, just by localizing and using the results there. So I think this it's also interesting to study this kind of systems. I think Professor Rabowski uploaded a couple of papers on the archive with this formalism. I think that adds some complications, and in my case, most of the results I have are local, so it wouldn't. I wouldn't get much more interesting results by working on this other setting. Maybe I'm wrong, but this is what.
No, I understand your point of view. It's clear that if you want to describe the evolution in terms of boundary condition, that is initial point and final point, which is your Q times Q, is clear this in general is not diffeomorphic to the cotangent bundle of Q.
Here.
So it's clear that the boundary value problem is not equivalent to the Cauchy problem of the equation. So what you have to do, you have to remove the offending part, let's say, because in general, the cotangent bundle need not be trivializable, so need not be accessible as Q times Q. But so the difficulties you are mentioning are due to the fact that you would like to describe your Cauchy problem, let's say, in terms of initial and final position. Now we know that already for geodesics, this creates problem because you may have focal points.
Yes.
So I don't question this aspect. I was more on the general side, let's say, saying that in a sense, this also to pick up what Alessandro was saying earlier, that to understand what is the role of the action and of the Lagrangian, we should really start from quantum mechanics, which in our understanding of the external world is a more fundamental theory than the classical one. So the reason why we are facing some of these problems is because we forget that the world is quantum. That's all.
Okay, I completely agree with your comment. We at least I think we should understand these systems a lot if we understood well the quantum version. But right now, for us, this is a work in progress. We might try to do something about the quantization of these systems and see how it relates to what kind of quantum systems. We even have some ideas of things that might happen. But also, this is just useful not only for physics. It has other applications on control theory, on optimization and things like that, which you are kind of independent from the quantum world. So in this thesis, I don't know, maybe the word quantum is in the introduction, but I haven't really dealt with it. I do think that we can gain some understanding even on this classical counterpart, but it's something that is widely open so far.
Okay, thank you. Thank you. In any case, I appreciate, as you already know, I appreciated all the work you have done.
Thank you very much.
Are you done?
Yes, thank you.
So now in section 4.5, reduction. Shouldn't this be momentum maths rather than moment math?
Moment maps.
Should it be momentum?
Momentum map. I've seen both wordings on the literature. I think I try to use a word consistently.
Yeah, you always use moment.
Yeah, but you can see both words on literature. I think moment appears more usually on more geometry oriented.
But in physics should be momentum. There's no.
Yeah, but there is like plenty of literature that they call it moment map. I guess no.
Okay.
I don't have anything now. Basically.
Okay. Could all this theory be applied to come up with Lyapunov functions for differential equations?
I don't know. This is something that we were thinking to work about, contact system and stability, but I have nothing on this. So I cannot tell you.
It seems.
Why do you what do you think what is the relationship between Lyapunov functions and?
Well,
No,
because you, if I understood correctly, one of the main motivations of all this theory is maybe go to page slide 6, whereas by the way there's also a misprint, a typo, because this q shouldn't be squared.
Which one?
In the last formula, the square
shouldn't be
there.
Yeah, exactly. It should be integral.
Yeah. Yeah. Okay. This is mass time acceleration. So if you put this through your formalism, you get various things that, in a sense, contract.
Yes.
And I feel that you should be able to combine the various things that contract to derive a Lyapunov function. So something. So you have like contraction for various things.
Yes.
Like for the Hamiltonian, but this is not a Lyapunov function for our purposes because the Hamiltonian depends on the action.
Yes.
but maybe you could combine all the things that you know that contract to come up with a function depending only on Q and Q dot. That could provide a Lyapunov function for this. So in this case, maybe it's trivial, but maybe your theory could be applied to derive Lyapunov functions for differential equations.
Yeah, probably the setting shouldn't be this one, but probably one of the Herbert's control problem, where here you are allowed to have controls. But I don't know, it probably yes, but this is something we haven't thought about.
No, obviously, this damped harmonic oscillator has a Lyapunov function.
Yes.
But it's not, just by looking at the equation, it's not easy to see what the Lyapunov function is, because it has a mixed term, mixing the P and the Q.
Yes.
If I rewrite it in the Hamiltonian way, the Lyapunov function mixes P and Q. And so it's not just kinetic plus potential as this Q term. And I just thought that since this theory provides so much insight into the things that contract and the rates and so on, you could combine them all to come up with a Lyapunov function.
This dissipated quantity, I'm not sure if it has something to do with
yeah, this is QP. Yeah, you need to put this
QP over 2 minus the action. This is dissipated.
Yeah, this is so you could combine. Yeah,
maybe there is a relationship.
So maybe you can now eliminate your Z from F. And I don't know. This is just something.
You are allowed to have this
in any case. So I think I should congratulate you and your supervisor for the very large amount of good work that you have put up for this thesis. And now any of the members of the panel or jury wishes to make an additional question or a comment or remark.
I don't have any additional comment.
That is the case. Any member of the public with a PhD degree would like to comment or ask questions? Well, in that case, this meeting is now adjourned, so you should leave.